Welcome everyone to our presentation this evening at the Sydney Central branch of Renew. My name is Mel Lupus and I'm the co-convener of this branch with Graham. Firstly, I'd like to acknowledge and pay my respects to the past, present and future traditional owners and elders of the whole nation. We're in the land of the Wongal people, which is part of the Eora Nation, and we acknowledge their sustainable management and care for country over many millennia. Tonight's presentation is on energy efficiency opportunities for common areas of apartments, and we have Ethan Burns here as our wonderful presenter. Ethan is an environmental engineer and director of Sustainability Now, an energy consultancy specialising in residential strata buildings. He's helped over 500 residential strata communities with practical energy and water efficiency solutions since 2009. Ethan has worked in the electricity generation, transmission and distribution industries for nearly 10 years prior to forming Sustainability Now. He regularly consults with the New South Wales Department of Planning and Environment on their NABERS for Apartment Buildings Energy and Water Rating Program and the City of Sydney Smart Green Apartments Program. Welcome, Ethan.
All right, thanks very much, Melanie. Welcome everyone. Let's get into it. Energy efficiency and solar and strata. Lately, we're framing this sort of thing more and more around NABERS and REI for apartment buildings. So NABERS is an acronym that stands for National Australian Built Environment Rating System. It's been around for, I think, 25 years now in the office sector, and it's been mandatory to disclose a NABERS rating at the point of sale or lease of office space over 1,000 square metres for, I think, 13 years now under the Commercial Building Disclosure Program. So this tool was adapted for residential strata in 2018. And it basically creates a level playing field so that you can assess pretty much any residential strata building in Australia on a fairly level playing field against each other. So whether that be, 300 apartments in Sydney with a centralised air conditioning system or 50 apartments in Hobart without an air conditioning system, you should be able to rate them on this 0 to 6 star scale and compare them so objectively. So we'll talk about a little bit about that. What are the key consumers of electricity or energy, in strata, so not just electricity. What changes can be made to reduce energy consumption and what are the incentive schemes available? And also we'll touch on solar as well. I like this phrase, a little bit of a cliche, you can't manage what you can't measure. So we like to try and establish a baseline of your energy consumption in the first instance to see where you are now, so we can work out where you're going and what you might achieve, and then compare what you've achieved against the baseline. So and also investigating the fluctuations. So it's good to try and take advantage of free services that are offered by your retailer, your electricity retailer. Most retailers have an online portal that you can access, and you can get set up there. You can download consumption data, graphs. You can make graphs. You can put in different date ranges and all kinds of different things. Unfortunately, some of the platforms are a bit clunky, but they're generally fairly intuitive. So have a chat to your electricity retailer and find out if that's accessible to you. And just understand how you're charged for your energy as well. Understanding how the tariff rates work can make a big difference as well. Here's an example, like just a little graph here of some daily load profiles for summer, winter, and the day of maximum demand. So this is just an example. You can see here, this sort of thing tells us a lot. So you can see these two peaks here in the morning and afternoon. This is from the car park ventilation system at the building. So they're set to run on a timer so that to coincide with perceived peak traffic movements. So yeah, this is going on here, and then here every single day of the year it does that. It's not compliant to the Australian standards, which say that those fans have to run 24/7 unless air quality is monitored. So in this particular building, we installed carbon monoxide sensors in the car park to control those fans, and then basically eliminated those 2 peaks. You know, the fans only run very briefly, very seldomly. Most modern cars are fairly efficient now in terms of emissions and that sort of thing. It's only if you get an old clunker really down there idling for a while where the CO levels get high enough to trigger the fans. So yeah, we basically eliminated those peaks. So that's just an example. Yeah, minimum daytime demand, you know, that's of interest for sizing solar systems and that sort of thing. So that's just one example of how you can use these tools. Here's another one as well. This is a couple of week period. No, actually a month. It's a month. So we can see what the normal sort of daily fluctuations in electricity consumption, but something happened here in this period. So in this case, I think it was the same thing again. It was car park ventilation system being overridden by the fire system. So whenever there's a fire alarm, the car park ventilation system's interlocked with the fire control panel, fire indicator panel, and it tells the fans that they need to run to get rid of the smoke out of the area. And if that's not reset properly, then it just runs until someone goes, oh, hang on a minute, we need to reset that. So there was a period of a couple of weeks here where those fans just ran flat out. So knowledge is power, I suppose, when you can sort of look at this information and you can actually act on it and do something. And a lot of these things, sometimes you can set up alarms and that sort of thing in them so that if it gets out of spec for any reason, then you get sent an email or something like that, or a text message. So that's quite handy as well. So NABERS, I touched on this before, National Australian Built Environment Rating System. Not sure why we need national and Australian in there, but it's in there. It's nationally recognised, 0 to 6 star rating, and it just measures your actual impact, not intent or design. So that's important. Green star, like green star ratings, you hear about buildings that have been like at the design phase that they've got a 6 star green star rating. I've seen quite a few buildings that were 6 star green star in design that ended up 0 star NABERS. So yeah, that's interesting. So yeah, it measures actual energy and water consumption. So yeah, it's a good tool. Mandatory disclosure probably coming within the next 5 years. I don't know if it'll apply to smaller buildings. There might be you know, a number, say they draw a line somewhere and say under 50 apartments, it doesn't apply. I'm not sure how that'll work, but at some point, that's where we're moving towards is mandatory disclosure at the point of sale or lease, similar to the commercial building disclosure for you know, for office space. So keep an eye out for that. So it's a good idea now to try and get involved with that now. Get your first NABERS rating. There's some good grants available. Like NABERS offers a grant where they'll pay for they'll basically pay for the lodgement fees for the first 2 years of ratings. So there's a bit of a discount there. It's about, I think, about $3,000 or $4,000 over 2 years worth of ratings. And if you do energy and water, $3,000 if you do energy only. It's called, if you want to Google it, it's called the Energy Starters Grant, NABERS Energy Starters Grant. So yeah, that's worth taking advantage of. Some local government areas might subsidise a bit more than that. Just check with your local council. So here it is, just a simple 0 to 6 star rating. And there's half star increments as well. So you can get 0, 0.5, 1.5, all the way to 6. Now, something that's new this year is Renewable Energy Indicator, or REI. That only came in June. So basically, it just tells you how much of your energy mix of your apartment building comes from a renewable resource. So everyone in New South Wales gets a default of 19% if you've only got electricity at the moment. So it doesn't matter who you get your electricity from, you get an automatic 19% to start off with. And then if you've got gas in there, it dilutes it from there. So your REI will plummet the more gas you use, because there's no such thing as green gas. It is all from fossil fuels. So the only way to improve REI is to purchase green power. So if you had just electricity supplying your common property, you didn't have any gas, and you purchased 81% green power, that would get you to 100% REI. So that's the simplest, easiest thing to do, like really, really easy. And most buildings I work on, I always do this calculation when I'm doing my report. I give them an estimated cost of what it would cost them to purchase 81% green power to get to 100% REI. And then I divide it by the number of apartments in the building just to give people an indicator of what is it actually going to cost me. And I quite regularly see it's $15 a year or something like that per apartment, $15 per apartment per annum. So that is your best, like, end of pipe, easy solution to just, lower your carbon emissions of your apartment building right off the bat, is purchase accredited green power. I highly recommend you do it at home as well. I think it costs me $35 a quarter or something like that. So yeah, it's not a lot in the overall scheme of things, and it's nice to know that it's all coming from a renewable resource. Also, you can do on-site renewables as well. Put a PV system on your roof and use that to offset your daytime consumption of your common property. Put a battery in and use it to offset your nighttime consumption as well. We'll talk about that more in a minute. So here's what the certificate looks like. This is a NABERS certificate. This is a building I just rated recently. So you can see it's 13th of October, 5.5 stars energy and 42% renewable energy indicator. So that building had a solar system. They got about a 25 kilowatt solar system on the roof. And yeah, so they're doing really well. Okay, so where do you use your energy in a strata building? Oh, there we are. Centralized air conditioning, if you've got a central air conditioning system. Not that many buildings, some of the newer ones in the sort of central Sydney do, but probably not that many on average have a central air conditioning system. Car park ventilation system, as we talked about before, if that thing's running 24 hours a day, then you've got a really easy win there. The carbon monoxide sensors will pay for themselves in about a month if you were to do that. Older lighting technologies, probably not too many buildings out there that are still running fluoros in the car park and fire stairs, but if they are, again, you're probably looking at a sub 12-month payback period on upgrading that to an LED batten with an integrated sensor in it that dims down to about 20% of full power when there's no one around. You'll probably find that it's brighter in there on dim mode with the LEDs than it was with the fluoros on full power. So I still see buildings out there that are still running fluoros. There's a great New South Wales government program called the Energy Saving Scheme at the moment and there's one in Victoria as well, the VEET system that basically, the subsidies are amazing on it. So yeah, you could probably replace a twin fluoro batten in a car park in Sydney now for, parts and labour for $50, something like that. Not even that sort of money, $30 to $50 or something like that under that scheme. So it's worth taking advantage of that. And that's actually winding back slowly as well at the moment. So I'm not sure exactly when, but I feel like maybe next year, those rebates might be sort of winding up. So it's good to get in, while that's still available. Pool heating, if you heat your pool, obviously that uses a lot of energy. And if you don't use a pool cover and it's outdoors, then it's just wasting a lot of heat. The age of the building can have a bearing on it as well. And contrary to what you might think, some of the older buildings actually are more energy efficient than some of the newer ones. And the reason for that is just bells and whistles. There's a lot of the older buildings just don't have the bells and whistles that the new ones do. So they don't use as much power. And I'm talking about common property here as well. So that's not to say that an older building is more energy efficient inside the apartments. It's probably not. It's probably thermally not as robust as a newer one. But so we're just talking about common property. Also, if the developer has an ongoing interest in paying or doing the operation and maintenance of the building and paying the bills, that probably has a bearing on what sort of plant they might install. Most of the time, it's the absolute bare minimum to meet the National Construction Code is what goes in. But there are a few developers out there that are sort of thinking ahead and trying to make their buildings more efficient right from the word go. So the biggest users of energy, like I said, centralized air. If you've got a chiller system or a condenser water plant, that sort of thing, they're always going to use the most. Other mechanical ventilation, like your bathroom and kitchen exhausts, those things, the Australian standard 1668.2 says that they need to run 24/7 unless you can monitor occupancy in those spaces. So there are some newer buildings that have basically the ventilation systems hooked up to the lighting circuit. So if everyone in that stack has their light turned off in the bathroom, then it'll shut down their ventilation fans for that. But as soon as one person turns it on, then it comes on again. So that's a kind of a newish innovation. Lighting, lifts, pumping water around the place, and then just miscellaneous motors and that sort of thing. Here's a little pie chart. Look, this is just an example from a report of where the various bits and pieces are used. That chart's probably a couple of years old now, and the lighting component's probably a lot lower of that pie now because with as the transition to LED lighting happens. I think there was 100 apartments or something like that. Yeah, that was just for one building. Yeah, it's not averaged over many buildings, no. Yeah, cold water pumping, yeah. So in this case, I think they had a header tank up where they pumped a jacking pump where they pump water up. And then it's gravity fed down to the lower floors. But because the head's not quite enough, they have to actually pump for the first few floors as well. Like they have to have pressure pumps up the top. So they're pumping it from the ground up to fill a tank, and then they're pressurizing it again up the top to do the first few floors, and then it's gravity fed from there down. So yeah, there's a lot of pumping of water in high rise goes on. All right, low hanging fruit. So low or no cost opportunities. We like these. Find out what your, if you're on the right network tariff. So there's sort of two main components to your electricity bill. There's network fees and then retailer fees. So the network fees shouldn't change with retailer. Doesn't matter who you're with, you still pay the same base fees to Ausgrid. You don't see that on your home electricity bill because it's a bundled bill. It's all bundled into the single rate. But if you've got a bigger building and if you use more than 100 megawatt hours a year, you'll see that unbundled. There'll be lots and lots of line items on there, and there'll be some network fees in there. So making sure that you're on the correct network tariff. The brackets go from 0 to 40 megawatt hours, 40 to 100, and then 100 to 160, and then 160 to 750, and then 750 plus. So there's a few network brackets there, and I, fairly regularly find buildings that are on the wrong network tariff, and then we just put in a form to Ausgrid, and they say $4.5 grand a year, that sort of thing on their bills. It's pretty easy. The network tariff brackets for New South Wales, this is just the Ausgrid area, Ausgrid network area. 0 to 40, 40 to 100, 100 to 160, 160 to 750, and then 750 plus megawatt hours. And those tariff things are EA 225, EA 302, EA 305, and EA 310. EA stands for Energy Australia, which is what Ausgrid was before it was split up, and Energy Australia was the retail arm sold off. So yeah, optimize what you've already got as well. So monitor and maintain, and use timers and sensors and that sort of thing to control loads that don't need to be on all the time. So again, we talked about T8 fluoros. In fact, I think these things here could be T8 fluoros in there. T8 just means tubular 8/8 of an inch in diameter. It's an old American lighting standard. So they're 25 mil tubes, the old ones that you used to see around the place. So if you still got those, or even T5s, which is the more modern version, the skinnier ones, 5/8 of an inch diameter, upgrading those to an LED with a sensor, integrated sensor, if you're just replacing a T8 to an LED, 60% savings automatically. Add the sensor, and if it's in a fire stair, 90+% savings. So easy. Halogen downlights. I haven't seen a halogen downlight in a long time, so there's probably not too many of those. Although I did see a shop the other day that still had halogen downlights, which is amazing. Yeah, there's probably not too many of those left around. CO, carbon monoxide sensors on the car park ventilation system, variable speed drives on pumps and fans. So a lot of centrifugal pumps and fans don't need to run flat out all the time. You can actually achieve the same thing at a lower speed. So for example, like a pool pump or something like that, you can still, if you have to achieve a certain volumetric flow, X number of litres a day filtration, you can do that at a lower speed and a lower litres per hour just for more hours, and that will save. Similarly with the car park ventilation fans, you can run the fans a little bit slower and just move the air more slowly. So the rule of thumb with centrifugal pumps and fans, if you slow them by 20%, you get a 50% power saving. So VSDs are really good for that. All it does is just alter the frequency of the incoming electricity to the motor, and that slows it down. Power factor correction. I haven't done a power factor correction unit in a while. So power factor, it affects your peak demand charges if you're on a demand tariff. So any buildings that use over 100 megawatt hours a year will probably be on a demand tariff. So not only are you billed for consumption, kilowatt hours, and your daily dollars per day fees, you're also billed on KVA demand, so the instantaneous load that the building puts on the network in the period, the peak billing period, 2 to 8 p.m. Monday to Friday. When you hit a new high, it resets and goes for another year. It's called a 12-month rolling maximum, so it's fairly punitive. Other jurisdictions do it differently, but yeah, it's a good one to avoid. So power factor correction will help you lower that, but it's not as necessary anymore because of the LED lighting. Like the old fluoro lights used to create bad power factor in buildings, but since everyone's gone to LED, power factor seems a lot better. Yeah, so the question was what causes bad power factor? And it's inductive loads. So motors and older motors that don't have capacitors built into them, and old fluoro lights with magnetic ballasts. So we don't have the old fluoro lights with magnetic ballasts anymore. So that's why power factor is kind of a non-issue these days. It's pretty rare to see bad, unless it's like some big old motors that are running in the place that don't have the capacitors built into them. And power factor correction unit's a very simple thing. It's just a capacitor bank that sits on your main switchboard and basically, lowers your reactive power. So the ratio of kilowatts to kVA is close to 1. But I regularly see overall reduction in consumption and costs between 10 and 40%. But every once in a while you come across a building that I think 90% doesn't happen very often, but quite regularly 40% savings we can achieve. All right, your electricity tariffs, take advantage of time of use billing. If your house lights or your common property power is still on a single rate tariff, more than likely you can make a saving just by switching to time of use. So your electricity price varies by time of day. You'll have a peak, shoulder, and off-peak period. And if you can shift any of that load, any sort of discretionary loads to the off-peak period, then you can make a big saving. For example, we talked about carbon monoxide sensors before and car park ventilation fans. Australian standard 1668.2 says that those fans can be turned off if you monitor carbon monoxide levels. Otherwise, they need to run 24 hours a day, 7 days a week. If the fans don't run on high CO alarm once a day, then you need to do one air change in the car park. So what you can do is schedule that air change for off-peak billing periods after 10 p.m, between 10 p.m. and 7 a.m. And then you can also install a variable speed drive on there so that you do it at a lower rate, at the minimum rate that fan can move air. You'll have a fan or a pump curve that shows you when you get to a point, if you go too slow, then it just won't move any air. So you can get it to set it up so it will just be on that point of where it's moving air effectively, but running at minimum speed, and then just do it for as long as necessary to do one volume change in the car park and do it in off-peak periods. So that's a good one. So your electricity consumption is billed in kilowatt hours. And I talked about this before, your demand, your electrical demand is billed in kilowatts or kVA. So there's a little weirdness there in that, if you're using between 100 and 160 megawatt hours, you're billed in kilowatts for demand. So power factor is kind of irrelevant to you financially. But for the bigger sites that are over 160 megawatt hours, you're building kVA when power factor is definitely of interest to you financially. Although Ausgrid has a network standard that says you shouldn't have a power factor lower than 0.9 at the main, at the supply point to the site. So they can compel you to install a power factor correction unit if they find that your power factor is below 0.9 at the main switchboard. I don't think they do that anymore. They did have a program where they were sort of actively, incentivizing buildings and that sort of thing to install power factor correction, but I don't think that's happened for a while now. There is a demand reduction program as well that runs in parallel with the energy saving scheme, the New South Wales Energy Saving Scheme. And there might be some power factor incentives on there as well. All right, so how do we save electricity? Number one, reduce the hours of operation. That's the easiest thing. Just don't run it as much if we can. So we can use timers and sensors. So the car park ventilation is a good example. Again, using the sensors to not run those fans if they don't need to be. The other way, so electricity consumption is a combination of electrical demand times time, like multiplied by time. So kilowatts times hours, kilowatt hours. So reduce one of those and you'll reduce your consumption. Reduce the hours or reduce the actual wattage, the consumption. So slowing the pumps and fans with VSDs, replacing them with more efficient technology. Just replacing a motor now, buying a modern motor, electric motor, it's probably 40% more efficient than it was 10 or 15 years ago, that sort of thing. So just the general technology in these things is much better than it used to be. So there's a thing called MEPS, Minimum Energy Performance Standard. So yeah, they're constantly getting more efficient. Retrofitting and just doing your general maintenance, things will always, run more efficiently if you maintain them as per the manufacturer's guidelines. So saving gas, I guess we kind of want to just try and get off gas completely if we can, but until you can sort of do that, then try and minimize it. So electrifying your hot water system. So you might have a central gas hot water system. Replace that with an electric heat pump system. Not super straightforward and simple. Some cases it is, sometimes it's a bit harder. Similarly, pool heating. An electric heat pump is, 3 to 6 times more efficient, thermally efficient than a gas heater. So you'll make some massive savings in terms of heat, but also some financial savings as well. Pool covers. If you haven't got a pool cover on your heated pool, then you're really just wasting electricity. And also reduce the thermostat temperatures. Does that pool really need to be as hot as it does? It need to be at 28 degrees? Can it be at 26? That sort of thing. Similarly with air conditioning, if you've got air conditioned areas, how cold or how warm, how cold in summer and how hot in winter does it really need to be? Fuel switching. Traditionally, gas has been cheaper than electricity, but it's interesting. The gas price hasn't gone up as much as I thought it might. Like last year, there was like a real bloodbath in the electricity market. I saw some clients' electricity tariffs go up by 250%. They just came off 3-year contracts. They might have had a blended electricity cost of about 10 cents a kilowatt hour for those bigger consumers. And they went up to 25 cents a kilowatt hour. And yeah, it was, it was crazy times, but I sort of expected gas to do the same because a lot of it is pegged to gas. So like my understanding of what happened was, obviously there were a lot of floods last year. A lot of coal mines got inundated with water and they couldn't actually extract the coal out of those. Callide Power Station, Callide B, I think Callide C, was it? One of the turbines blew up in like a major 400 megawatt turbine went offline. So that created a bit of a supply and demand. There was less supply, demand stayed the same. So that caused prices to go up. They couldn't get the coal out of the ground to put it into the power stations because it was underwater. So they had to rely on gas, so gas turbines and that sort of thing, which you kind of thought would drive the gas price up a bit. Ever since the East Coast has we've started refrigerating gas and turning it into LNG and shipping it offshore, we've had a lot more exposure, I suppose, to international gas prices and that sort of thing. But gas doesn't seem to have gone up, at our sort of level, at the consumer level. It doesn't seem to have gone up as much as electricity has. But I just don't think that can last going forward. But even so, even with that, you still get a decent return on investment on replacing a big centralized gas hot water system with a heat pump system. Like it all depends on the actual building, because it is a bit trickier to install them. They need a lot more space. They're bigger. They need better airflow. You need a decent electricity supply to them, and that sort of thing. So there's a few barriers there, but I've seen payback periods as low as on very small buildings. As low as 3 years, that sort of thing on heat pumps. Maybe 5 years on a bigger building, 5 to 10 years on a bigger building sometimes. So the other reason we might want to switch fuel, obviously, there's no such thing as green gas. There's talk of putting hydrogen into the pipeline and that sort of thing, green hydrogen. The pipelines can only handle 5% hydrogen until they brittleize and crack, and there's all kinds of problem there. So, and also then you have to change your appliances as well. They won't burn properly with a higher mix of hydrogen. So, coal seam gas has got its issues as well with fracking and aquifers and all that sort of stuff. So better to just start thinking about transitioning away from gas as soon as you can. Electric, like I said, electric heat pumps potentially greater than 5 times more thermally efficient. Similarly, hot water system, pool, like a gas hot water system or a pool heater might be 80% efficient, 85 if you've got a really good one. So it effectively means that if you put 1 kilowatt of gas value or 1 megajoule of heat into that thing, you'll be lucky if you get 0.8 of a megajoule of actual heat out of it. Whereas a heat pump, you might put 1 kilowatt of electricity in and get 4 to 5 kilowatts of heat out. So much better. Okay, so maintain your standards. Just while you're doing all of this stuff, don't cut any corners. Make sure that you're meeting AS 1680, your general light levels around the place, AS 2293 for emergency lighting, and then 1668.2 for mechanical ventilation. Make sure that whatever you do still meets those standards. All right, government incentives. Ask your local council. That's your first port of call. Get on your council website, call your sustainability department at the council and find out what they've got on offer. So at the state level, we've got the New South Wales Energy Savings Scheme. I've talked about that before. There's some great incentives, especially around lighting, particularly around lighting. There's some great opportunities there. There's a Victorian one as well. And then there's a federal renewable energy target, which we probably all know about. It's been a great program, that. I think it's really hard to fault that one. I think it was really well designed and set up. It kind of, basically they'll give you a rebate on installing solar and heat pumps and that sort of thing. And it sort of reduces every year. So it drops down on 1 January each year. The number of STCs that you can generate from your solar system drops off. But it's kind of designed to to sort of match the drop in natural cost of solar as well. But it's kind of plateaued a little bit actually in the last couple of years. And actually, maybe the last 2 years or so, the solar cost has kind of plateaued a bit. And actually, it might even be sort of creeping up slightly now. So, yeah, if there's ever been a good time to get into solar, it's now. Speaking of solar, so where do we want to put it? We want to try and, in the Southern Hemisphere, have it on the north aspect, if you can, of the roof. East and west is also okay and all good. You don't get quite the output in winter because the sun stays in a low arc across the north sky. You get a bit of a reduced consumption if you're on east and west. Avoid the south. It's funny, I was actually up in Queensland not that long ago on the Sunshine Coast, and I was driving along and I was driving north and I saw this brand new massive, McMansion house, and the solar panels were on the south aspect of the roof. I was just like, what's going on here? I couldn't believe it because there was nothing, all the other ones in that estate, you couldn't see any solar on the roof. And when I came back the other way, you could see it was on the north roof of all the others, but whoever installed it just got it wrong and put it on the south aspect of the roof. So that was interesting. Yeah, so you can get an STC or an LGC rebate. So this is under the renewable energy target that I mentioned before. So STCs you get on systems that are under 100 kilowatts, and that's a nice upfront discount. It's usually delivered as a point of sale rebate from the installer. So effectively you sign the STCs over to them, they aggregate them, and then they sell them when they think the market's high and that sort of thing. LGCs is slightly different for systems over 100 kilowatts. You have to sort of put a claim in every year for that one, so it's a little bit different. Micro inverters. Okay, so most solar systems that you see are installed with string inverters, where you have lots and multiple panels that all go into one big box that converts it from direct current at the panel to alternating current that you can use in your power points. But if you've got a building that's got shading issues and that sort of thing, I guess the issue with string inverters can be that if you get enough shading on, one or two panels or something, the voltage can drop enough that you'll lose the whole string. Micro inverters are good in that you can isolate. If you lose one panel, it won't have any effect on the you'll only lose that panel. It won't take out a whole string. So they're good, but they're also good for apartments in that, this is one example that I was involved with. There was a building in Bondi that had 5 apartments, and they had a really nice north-facing roof that was just the right size for a 10 kilowatt system. And basically we set it up so that we had a big 10 kilowatt array up there and split it up using micro inverters. So everyone got 2 kilowatts, each apartment got 2 kilowatts. It was really good, worked out quite well. So they're good for that sort of thing as well. I mean, you could have done the same thing with string inverters as well if you had enough room for 5 string inverters. So yeah, they're handy for that sort of thing. Where you've got taller buildings, it gets a little bit harder. You've probably got to get a crane to get the panels up there. Also, the wind ratings at high over 20 meters, you need to get like a specialized sign off on the. There's not the mounting systems aren't automatically certified for those sort of things. So there's a few things you've got to do, extra things you got to do with strata just to make sure that you cover all your bases. Again, you want to make sure that your roof's in good nick before putting solar up there, because you don't want to put solar up there and then 2 years later have to replace your roof and take it all down, that sort of thing. So get a roof dilapidation report done before you put the solar up there and fix anything that might need fixing before you do that. Yeah, so, payback periods. I'm regularly seeing payback periods in a 4-year sort of mark now, which is amazing because it's a 20 to 25 year installation. You should be able to put it up there and hopefully not do anything with it, for that time. There's a couple of schools of thought as to whether or not you should do preventative maintenance on the systems or not, or whether if you install a decent monitoring system that will tell you whether or not, it'll tell you and alert you if your system's not generating what it should, like solar analytics, for example. If you were to have that on there, that kind of tells you when you need to do your maintenance. If it's not working for some reason, that's when you do your maintenance. So you can potentially avoid or you can just do a clean and check, once a year to make sure. So, but yeah, really compared to a lot of other things, they're kind of set and forget a little bit, as long as someone's watching the monitoring system. Batteries, everyone's talking about batteries and has done for ages. They're getting it's hard to find a system where they'll pay for themselves within their within their design life, within 10 years. It does happen though, if you've got a time of use tariff and you can charge the battery with excess electricity that would otherwise be exported to the grid that you get kind of next to nothing for. You know, you might be lucky to get 10 cents a kilowatt hour for that electricity that's exported to the grid, whereas what you're bringing in is costing you 25 cents a kilowatt hour, something like that. So if you can store that in a battery and then discharge it during your peak billing period, for which you might be paying 50 cents a kilowatt hour, then there's a nice margin of about 40 cents a kilowatt hour there that can help pay that battery back in, you know, in less than that sort of, less than its design life. So it's definitely a prospect for some buildings, if you can fit enough solar up there to the point where it will export to the grid. So there's three main ways that we connect solar to a residential strata complex. And the most simplest way is just feed it into the common property meter. You can also do the same thing. Like, so that place in Bondi that I just talked about that had 5 apartments, it was an old walk-up sort of red brick type thing, old. There was nothing really on during the middle of the day. There might have been a couple of exit signs or something like that. So their daytime demand for the common property was next to nothing. Like, it wouldn't, one panel would have been an overkill for that. So for them, it made more sense to just send it all to the tenancies. But, you know, if you've got a bigger building with lifts and pools and fans and all that sort of thing, then it's using a lot of electricity during the day. So it all just depends on what type of building you're in, as to how you do it. One of the other problems that you can face, though, as well, if you're sending electricity from the solar system to the tenancies, is that Australian Standard 4777 says that once you get over 30 kVA or 30 kilowatts of inverter size to the one connection point to the grid, then you need grid protection relays on there. So additional protection. And then if you have multiple systems installed at that point of connection, then you need multiple relays. So you need a master relay and sub relays, and that can start getting very expensive. So that can be a problem with connecting to tenancies if you have multiple systems on there that add up to more than 30 kilowatts. But there's a good way to get around that, which is a loom. And that's if you've probably heard about that. It's another special box that allows you to put a very big solar system on there and have one inverter. So you might have a 50 kilowatt system up there with one inverter, and then it feeds into this loom box that then distributes it to each tenancy. So that gets you around that 30 kilowatt thing. So you only need one relay on that system, one grid protection relay, and then it does it all behind the meter. So it's quite expensive though. It's about 15 to 20 grand, say, for the box that can distribute that solar to 15 apartments, 15 single phase connections or 5 3-phase connections. So the ideal is if you had a building with 14 apartments and one common property meter, you'd have 14 tenancies connected up to that box, and then one phase also going to the the common property meter, and that would be full utilization of that box. And you can stack the boxes as well. There's a building I worked with in Alexandria that they had 45 apartments, so they put 3 of the boxes on. And yeah, so all 40, they put a 70 kilowatt system up there. So all 45 apartments are getting solar from that. So there, that's a good project. If you've got enough roof space to support, I mean, on a block of 6, your common property is probably not using much at all during the day. Yeah, so it's probably better to send it to the tenancies. I mean, you could install one of those loom boxes, but you'd only be using 6 or 7 of the 15 possible connections on there. So you're not getting as good a value, I suppose, as a building that has 14 apartments who are using more, but you could use one of those. The other good thing about a loom too is that it actively sends power to who needs it. So it's constantly monitoring what the demand is on each of the connections. And if you're got your washing machine going and your neighbour's out for the day, it'll send the power to you. And then if you're out the next day and your neighbour's doing their washing, it'll send the power to them. And then it tries to balance up the ledger towards the end of the month. So it's actively sending electricity where it's needed. So it's quite smart in that way. Whereas if you just had like the Bondi example where everyone just had 2 kilowatts, that's kind of a dumb system because if you're not home, it'll just send it back to the grid and you get your feed-in tariff for it. But your neighbour might be, needing more electricity, but there's no way for them to actually access it. So that's a good thing about a loom. But your building with 6, if you've got enough roof space, then you might look at, doing that, where you have a large array up there and then split it up 6 ways. But yeah, if you wanted just exclusive use, then you need to get a bylaw. The bylaws aren't expensive though. Like there's an off-the-shelf one that you can buy. Just Google strata solar bylaw, and there's a few of them come up, $200, I think, something like that, for that bylaw, and you can just edit it and add the bits and pieces in there as necessary. So yeah, I think it's definitely worth doing. Yeah, it's sometimes easier on smaller buildings than it is on bigger ones. Green power. We talked about that a little bit before. Look, it's the easiest thing. And I kind of think my personal thing is just do it now, do it straight away. And then, all your electricity is coming, your allocation of electricity is coming from a wind farm, solar farm, that sort of thing. And then when you're working on your energy efficiency initiatives, you're just buying less of it. So it's costing you less as you improve efficiency. So it's the only government accredited program. Solar and that sort of thing is not practical in all buildings. So yeah, green power is the only accredited program. It's the simplest and easiest way to access renewable electricity. Most retailers offer it. Just beware though, some of them offer offsets instead of, they're not accredited green power. They'll call it something that sounds kind of similar, but it's actually an offset, which some of those are pretty dubious, like where their sources may not be that legit. So yeah, you might have noticed Energy Australia a couple of years ago said, we'll give you free carbon neutral electricity. You don't even have to, all you have to do is opt in for it. We won't, charge you anything for it, which is great. It's better than nothing. You might as well opt in for that. But I don't know. I'd be questioning the veracity of the carbon claims on that. So yeah, green power is also good. It's a price signal to the government and says we want more renewables, and it'll also have a direct impact on your renewable energy indicator if you get it for your common property. So it will help that. All right, EV charging. That's so hot right now. It's really. Everyone's talking about it. So just last week, I think it was, the New South Wales government opened up their grants program where they will basically the end game for this is that you can get matched funding of 80% up to $80,000 per building to install EV charging. But in order to access that funding, you need to have a feasibility study done. Which they've capped the price at $2,000 on that. So there's a panel of 5 assessors who are doing those. You put in your grant application and say, we want the feasibility study. They'll allocate it to an assessor. You pay the assessor $2,000. The government pays the balance of whatever that might be. You get your report, then you go out, get some quotes to install your EV charging. You submit the grant again, do another grant application to them again, and then hopefully they'll come to the party with 80% of the cost of that infrastructure up to $80,000. And I think that also includes main switchboard upgrades as well. Most older buildings will need a main switchboard upgrade in order to do this. And I think you can claim the cost of that as well under the program, as long as you're doing EV charging as well, like installing EV chargers. So it's open to all Class 2 buildings, which is residential strata buildings, but you have to have at least 10 apartments, unfortunately. So unfortunately, the small buildings kind of miss out on that. Also, if you have more than 4 EV chargers installed already, then you're not eligible either. So there's a link to this coming up. Okay, so the question was, is there any way to check if your existing infrastructure, electrical infrastructure, your main switchboard and that sort of thing can handle EV charging before you commit to spending the $2,000. Look, you could take some photos of it and you know, or maybe get an installer out to do a quote or something like that and see what they say. And they might tell you whether or not it works. But honestly, most older buildings probably going to need a main switchboard upgrade. The first limiting factor is going to be, do you have enough space on your electrical distribution board or your main switchboard on the chassis? Is there actually a spot for a circuit breaker to go that can handle the EV charges? That's the first roadblock. And then from there is, you know, how much can that main switchboard handle where the electricity comes into the grid? And then the next problem from there on is, can the substation that's supplying your building handle that extra load? That's where it gets really hard. You can put, I think it costs several $100s to make an application to Ausgrid to get that checked. And the other problem that you have as well is a lot of these older buildings don't have a main switch coming into the site. They've just got cables coming straight from the substation into the board. So there's, you know, it's not easy to tell what the maximum demand of the site can be before you're causing problems downstream. So that is hard on these ones, on some of these buildings. You've basically got to look at the cable diameter and the distance and that sort of thing and do the calculations on it. So, and this government program, the feasibility study basically assumes that everything's okay upstream of there. So it won't go into that, unfortunately. For example, if you had a building that's got, you know, a lot of the smaller buildings around here might have a 200 amp supply. So they've got 200 amps to the common property, 100 amps to the common property, and 100 amps to the tenancies. So you can see you've got a main switch that's that size. Theoretically, you know, and I guess under this program, we're assuming that you can pull 200 amps at that point and everything will be okay. So that's kind of what we're running with on that. All right, so challenges to consider in strata. There's, you know, you guys know about this if you live in strata. There's several decision makers, not just one. A lot of the decision makers might lack technical or business background. So it's hard to sort of talk in payback periods and ROIs and that sort of thing. There also is quite often some extremely irrational people who might be on your committee and just they're impossible to deal with. I've seen some wild strata committee meetings in the time I've been doing this. There's definitely some personalities to manage in there, so I don't know what you can do about that. There seems to be a bit of an aversion to opportunities that take more than 2 years to pay for themselves, especially for investor owners, you know, who might be thinking about flipping that apartment in the next 6 months and that sort of thing. They don't want to spend any money. But there are things that can help with that. You know, lack of financial incentives compared to businesses, you know, might get better things. But this sustainability infrastructure resolution is a little bit of a game changer. I think it came in maybe 3 years ago, something like that. So it's a slight modification to the Strata Schemes Management Act. So it's a subset of a special resolution, which you would take to a general meeting. And it's carried if not more than 50% of the people present at the meeting based on unit entitlement are against it. So with a normal special resolution, that number's 75%. So if you get, it takes a little bit of getting your head around. So if you've got, let's say 10 people at a meeting, you've got, and they all have equal lot entitlement, equal unit entitlement, and you put a motion up to install solar on the roof. And 4 of those people at the meeting are against it. 4 are for it, and 2 abstain, then it's passed, essentially. So if less than 50% of the people present based on unit entitlement are against it, then it's passed. So I think it's helping get these sort of programs up. So solar, LED lighting, anything that has a positive environmental impact. Again, I've got a link to the Strata Schemes Management Act where it talks about the Sustainability Infrastructure Resolution. You can read it. It's written in legal speak, obviously, but it's reasonably straightforward. All right, so here's some case studies. This building, 43% electricity savings in Chatswood, 255 apartments built in 2001. We did a large LED lighting upgrade of all the common areas, put carbon monoxide sensors on their car park ventilation fans. They had massive fans there. They had 2 75 kilowatt fans. So that was really easy. They had a condenser water plant as well, which was running 24 hours a day, 7 days a week, pumping water around the building to take heat away from air conditioning, packaged air conditioning units. So like these ones up in the bulkheads up here, because there's nowhere convenient in most apartment buildings to put an outdoor air conditioning unit. So like if you think about a split system air conditioner that's air cooled, you have an indoor part and an outdoor part. So the heat gets taken out of the room and then blown out into the day via a fan. Because you can't, there's a lot of buildings that there's no space for that outdoor unit. They basically have a water heat exchanger in there and they run a loop of water around the building that takes that heat and takes it up to a cooling tower and then sends it away. So heaps of these were installed in the 90s, and that's 90s and early 2000s, before VSD technology really took off, and they just run flat out 24 hours a day, 7 days a week, 365 days a year. Even in the dead of winter when no one's even using their air conditioners, these things are just running. So putting some smart controls on those to wind them right down and turn them off completely in winter, and also wind them down with demand as well. So putting like pressure transducers on the pipework, putting control valves on the actual air conditioning unit. So when no one's using it, there's a little motorized valve that shuts off the water to that unit. Pressure builds up in the pipework. The pressure transducer reads that and goes, hey, we don't need to run so fast, tells the VSD to slow the pump down. These sort of things, massive savings. We did that there. We did a power factor correction unit. Yeah, we reset their peak demand, and yeah, they saved 87 grand a year, 87.5 grand a year. So the payback period on those sort of things was like the lighting payback period was, I don't know, less than 2 years. Carbon monoxide system, again, less than 2 years. Condenser water pump was probably about 2 to 3 years. And the power factor correction unit, I think, was 18 months or something like that. So these were all really fast payback periods on this one. So this is what their demand profile looked like before and after. You can see, so there's the car park fans. They were running for like crazy times as well, like from 6:30 in the morning to like 10:30, and from like 3:30 to 7:30. Just insane, like massive overkill. Look at the demand difference here. 150 kVA was their base load to 250 kVA up in the middle of the day. So there's 100 kilowatts of extra load there that we just chopped out. So that the carbon monoxide sensors fix that, but then we also dropped their base load by by 50 kVA as well, and that was the condenser water pumps. So basically running those a lot lower, and then they've just got a few little spikes here, which some of those could be the car park fans just kicking in as they need to, rather than. So it's actually safer as well, because if some old car started up down like in the lower part of the basement and ran idle for a while, that could have been creating, very unsafe air quality down there. And there's no way those fans could run because they were set on a timer. So if that happened outside of those hours, then people's health's, at risk. Whereas now it'll happen only when there's a bad air quality event.
Did you say before that
it is, well, it's not illegal, but it's not compliant to the Australian standards. And the reason people, I guess, did that was because they just cost a hell of a lot of money to run 24/7. So it's just an insane amount, an insane cost. So they just thought, well, look, what's a roughly risk-based approach that we can do. Most people, you know, are going to drive their car on their way. They're going to leave and go to work, you know, between 6 and 10 or something like that. So let's run them, put them on timer and run them there. And they'll come home around that same time. So we'll do that. Basically, that's how they were doing it. And also, I think the Australian standard might have changed at some point as well, post these sort of installations as well. So there's probably a little bit of grey area there as well. Yep. And these are just some pictures. Like, so that's the VSD, the variable speed drive, controlling that big pump there. That's the condenser water pump. Power factor correction unit. Pretty boring. Just looks like a box with wires coming out of it. All right, this is another good one. This is the building I was talking about with 45 apartments in Alexandria. They did an LED lighting upgrade. They put 26 kilowatts of solar on to do the common property, which was a massive overkill. They put 10 kilowatts on, and that was exporting to the grid like crazy. And then they went and put another 16 kilowatts on. And then they put another 70 on and connected that to the tenancies as well. So all those apartments receive solar during the day. None of them pay for any electricity during the middle of the day. They only import it at night. The next step for these guys is putting a battery on as well, because they're still exporting heaps to the grid. We changed their tariff bracket. We dropped them down a few tariff brackets because they kept saving more power and they kept dropping down tariff brackets. So they were saving heaps there. So this is just for the common property, 9,500 a year. They were saving, and 39 tons of CO2. They've got a 6-star NABERS rating as well out of that. So that was a good one. Yeah, 68% electricity savings. So it's really the only, the rest of that is just what they import overnight. So yeah, batteries next for them. Here's their demand profile. You can see it used to be like that in the middle of the day. And now it sort of goes up there. The sun comes up and then it just drops through the floor down to nearly zero. That's the average over a course of a year. In summer, it's way down here. It's negative exporting to the grid. And then, yeah, comes back up that way. This is just some cost graphs. So that was their baseline there, 166 kilowatt hours a day. When they did their lighting, it dropped down to 105, then down to 101. And then the first solar system was put on, that dropped down to 54. And then you can see their costs went from $37 a day down to like $11 a day. And that's in 2017. I should update this graph. There's more. There's a picture of their building and their solar system. Capella is another good one, 164 apartments in Kensington. Again, same things, LED lighting upgrade, 27 kilowatts of solar, power factor correction, capacity reset, $37,000 a year saving, 255 tons of CO2. Again, payback period on the lights, sub 2 years when this was done. The solar system was a bit longer payback period because it was done a while ago. It was about 8 years or something like that. But again, it's paid for itself, it's still generating. So it's a good one. That's their demand profile again as well. Like that's where they were up there. It's just a 1 day sort of thing, averaged over a year. And that's post, so you can see the solar takes a massive chunk out of their daytime demand. They haven't got enough solar up there to export to the grid though. Just didn't have enough roof space. So. Again, more pictures of solar and a nice building. That's right near Randwick Racecourse. All right, here's some links for you, some other resources. So the green power thing, this kind of just talks you through how to get green power. Energy Made Easy, this is a great one for your home as well as if you're on a smaller electricity tariff, on a small to medium enterprise tariff for your strata building, you can just look on your electricity bill and find your NMI, National Metering Identifier, National Meter Identifier. It's a number, 10 digits or so, starts with 410. And then you can go onto that website and just type that in there, and it will download your data for the last year, and it'll run a model, and it'll tell you who the cheapest electricity provider is, who's going to give you your best rates. It's run by the federal government, so no one's getting any kickbacks. It's all independent. So what I also tell people to do is have a look at this one as well, the Green Electricity Guide, which is run by Greenpeace, and that tells you who the most ethical retailer is. So I like to cross-reference those two things, because your cheapest retailer's not necessarily the most ethical. You know, Origin Energy Australia, they're like number 34, 35 on the list, down the list. So, you know, that's who most people are with. AGL, they're all in that sort of mid-30s tier. You'll often find that there'll be one that's in the top 3 that's in the cheapest as well. Energy Locals pops up a lot. They're in number 3, I think. Momentum, number 2. They pop up a lot when I'm doing these things. So yeah, just plug that number, plug your National Meter Identifier into that calculator, and it'll tell you who's the best. There's the legislation thing there. That's just a New South Wales link to tell you about the Sustainability Infrastructure Resolution. And this is the one for the electric vehicle grants. But if you just Google EV ready buildings, New South Wales, it'll come up. Yes, and that's it. I'll leave that up so you can sort of keep copying that down if you like. But any questions? Oh, thank you. Yep, good question. So small wind turbines, do I know of any buildings? I don't, and I know, but I've had lots of people investigate it. Someone can correct me, but my feeling is that wind turbines are really for, you know, out in big open fields. Big ones, little ones don't seem to do that well. They don't seem to cope very well with turbulent wind flow. They like nice, steady laminar wind flow. If it gets turbulent and gusty, which is, you know, most things around built-up areas, you get gusts. You don't get nice, smooth wind flow. There was a building in Balmain, on Balmain shores, that we're talking about trying to put some like marine-grade wind turbines, like you put on a boat. Put a heap of those up there. I'm yet to see. Do you know anything, Sonia? Yeah. Yeah. Oh, okay. Yep. Yeah. I was kind of hoping that might go ahead just to see what it would actually do, but yeah, I think. Yes. There you go. Yep. Because they would get a nice, like, nor'easters blowing through there would be pretty good, I suppose. But yeah. So yeah, I think it's, you can get the vertical axis ones as well, but I don't think they really generate much. Like that one that's on UTS, I think doesn't really actually generate anything, really. Yeah. Noise, yeah. Yeah. Yeah, that's another good question. Yeah, you definitely have to get sign off on a structural engineer for the mounting, like the weight of the thing, the point load, and also the flex that it would put on there. Yeah, the foundations and that sort of thing. Absolutely. Yeah, you'd want to get that all checked out. Ah, yeah, that's and I probably should have mentioned that actually in my thing. I think that can be a potential game changer if you can be, if you can have batteries and be involved in a virtual power plant, a VPP. So again, it's kind of a little bit of a gamble. So there's this thing called FCAS, Frequency Control Ancillary Services. So effectively, if you have a problem with the grid and maybe a generator falls offline or something, you get a massive spike in frequency in the grid, and they need to try and stabilize that really quickly. And they like to call on batteries to do that. So Ausgrid have got a program that's going at the moment where they've got a few people who are doing these things where they can basically remotely activate these batteries to do that frequency control thing. And the theory is that you have a battery installed and you just use it day to day, but in the emergency situation where they call on it, they'll use that battery, and then they'll pay you a premium to use that electricity. I've heard numbers of like 55 cents a kilowatt hour or something like that they'll pay you to use that battery. The problem is though that we don't know how often that's going to happen, I suppose. But what they do is they kind of forecast it on what happened last year. And they say, well, look, this is what happened last year. So, you know, if the same thing happens again this year, then that's what your FCAS revenue might be. So I had heard that it wasn't really that good for smaller battery systems, that it was really only good for like 200 kVA, 250 kilowatts of battery, that sort of thing, 250 kilowatts, which is much bigger than most strata buildings would install. But there was a company that was aggregating small ones around the place that seemed like it was, you know, interesting. I think they were called Powwow, or there was a Shine Hub, those guys. Don't know how it's going, but yeah, yep. I think FCAS could really, FCAS and being part of a VPP could really be a game changer in terms of you know, return on investment in batteries. Yeah. Okay, so the question was, there's an AGM coming up in 10 days. How do I present my sustainability things? I don't know, like, I wonder whether 10 days is enough, because normally they close like the agenda 2 weeks or something like that out for that. Yeah, okay, if you can get it in, that's great. With such a short sort of time period, I think probably going direct to an installer who does that sort of thing day in, day out, and getting a quote at least. And if people can see, look, this is not that expensive. On a building the size of 15 apartments is kind of tough. Like to take advantage of that New South Wales energy saving scheme, they probably want a minimum of about 50 lights. And there might not be 50 lights throughout your car park and fire stairs. So, yeah, but yeah, that's a tough one. Like, I think I wish I could point you to some resources or something somewhere where, like, go to my website and there's case studies on there, I suppose, about lighting upgrades and that sort of thing. And you could just get your electrician, your incumbent electrician who does the tube replacements. Yeah, absolute worst case scenario, like, or easiest case scenario, is as the old fluoro tubes fail, just put LED tubes in. It's not as good as replacing the whole fitting, but you'll get an automatic 50% saving by doing that. And that's just the simplest, like, easiest way. The LED tubes are not that much more expensive than the fluoro ones. So that's probably your, like, path of absolute least resistance, is just do that in the short term. Embedded networks are an interesting thing. So the concept of the embedded network is that if you've got, say you've got a building with 100 apartments and you've got a common property meter, so let's say 99 apartments and then one common property meter. So you've got 100 different electricity accounts in that building. So all the apartments are paying a premium for their electricity. You know, generally speaking, and it's not so much the case now as it used to be, but the less electricity that you buy, the more it costs on a unit basis. So, you know, you might be paying 25, 30 cents a kilowatt hour or whatever for your electricity in your home. Whereas prior to, I don't know, 12 months ago, the common property of the building, because it was using a lot more, might be paying 10 cents a kilowatt hour. So the idea is ring fence the whole building, put a gate meter on outside and pay 10 cents a kilowatt hour for everything that comes into the building. And then the owner's corporation, or effectively somebody else, become a quasi retailer where they sell it to the individual apartments behind the meter. So you have a private metering network in there. So you're not paying the higher sort of costs. Everyone, like all those 99 apartments, are paying network fees. So you're basically kind of removing those network fees. And theoretically, it's cheaper electricity for those apartments because you're sort of just paying that gate meter rate. So the issue is that there's infrastructure costs involved with that. You've got to take all the Ausgrid meters out, and then you've got to replace them with your own private meters. So there's a cost to that. And then also, who does the billing? So the owners corporation, I'm sure the volunteers aren't going to be interested in like sending bills out. And then also there's legal issues as well with if you've got a bill from the owners corporation for electricity and you're not set up as a retailer, potentially there's no obligation to pay that. Like people can just go, I'm not going to pay. So then you probably need to engage a third party, like an embedded network provider, who do have a retail license, who can do that for you. So my feeling is that they're the ones who are the winners in this because they have the billing rights and they basically clip the ticket that way. So I think it can work. I think it can, if it's combined with solar, like a really big solar system on the roof, then it can work really quite well. But since last year when the electricity prices went up, the gate meter costs are very much closer now to what everyone else is paying on a small basis. So, you know, you might be paying $20 cents a kilowatt hour at the gate meter and 25 cents at the consumer level. That margin is what makes you able to do it, and the margin's not there anymore, I don't think. So unless you have a really big solar system on the roof, so you're getting effectively free electricity from that solar system, then the margin's a lot better. There's lots and lots of buildings out there who had embedded networks installed at construction who are trying to get out of them at the moment because they're paying more than they would if they were just, you know, like everybody else. You can actually go out to tender for your embedded network a lot of the time. You can change providers and hopefully get a better deal with them. But the problem is that when the developer signed up that building, it was a good thing for them because they didn't have to pay to install all the electricity meters. The embedded network operator did, and they own those meters, those private meters. So you'll find something in the fine print of the contract there that says, if you want to kick us out, then you need to pay us for all these meters. So yeah, I don't know. I'm not a massive fan.
We've got one question online, which I think you've answered, but just to recap, about the project in Bondi with the 5 dwellings.
Yep.
The question was it done directly? And I replied that it was, and they're saying, well, why do that rather than a loom system?
On that building, just because there's only 5 apartments, really, and just they wouldn't have got full utilisation out of the Illume system. So the Illume box only comes in one size, 15, so 15 single-phase connections. And for that building, it would have added an extra $15,000 cost to the project. And yeah, that's really the effective, yeah. If you had 15 apartments, it's only an extra $1,000 each. It's kind of not so bad, but if you've only got 5 apartments, then it's $3,000 each. So yeah, that's really effectively why. I think they were talking about bringing out a smaller version, like 9 or something like that. I don't know how far off that is.
Thank you very much.
All right, thanks everyone.
I was just going to make 2 announcements. For members, if you're a member of Renew, the local branch will be having an AGM online on the 7th of December, Thursday night, the same time as now. If you're a member, you'll get an email about that. So yeah, and otherwise we'll be starting a program of these evenings from February next year.
Thanks very much for coming, everybody. Thanks again, Nathan.